Okay, this is day number 2 for prob and stats and distribution unit. We're not going to talk probability today. That's a misprint. We're going to talk combinations, permutations. So let's jump right in. First of all, before we get there, I want to talk about, again, the difference between the population variance and the sample variance. Okay, population variance, again, we call the mean mu, and the population, of course, is if we have the entire set, not just a sample of the set. And the notation, of course, this is a Greek letter, this is a Greek letter. That would be pretty standard for population notation for variance as well as mean. Now, what does this x sub I thing mean? Each individual point of the data set minus the mean, square it, and then take that sum and divide it by n, the number of items in the set. Okay, so sample will be different in this way due to the fact that we don't have the entire set. We're going to use a little bit different language with it. So x bar will be the mean, s, capital S squared, will be the variance, and of course then we toss that notation for x bar in, we forgot to square that, and then divide by n minus 1 due to the fact that we don't have the whole set. Okay, so this is our variance. The square root of that we would call our what? Standard deviation, right? So the standard deviation of a sample would be capital S. You might see that on your 1 var stats. You see a sigma and you see a capital S. That's the difference between population variance, population standard deviation and sample standard deviation. Okay. Okay, that should be a little bit of an overview from yesterday. This slide here has an example that I actually covered in the video from yesterday. It's some good practice with just the basics. I'm not going to go through it right now. I'd say probably the most valuable items there would be sketching the cumulative frequency graph and part G there, the word problem, where you add a few more items to the set and then you have to do manipulation. So that would be good to go there. I want to jump right into the multiplication principle. And the multiplication principle it's related to combinations, permutations, but it's kind of a unique side note. Okay, so let's say we're registering for one of 3 physics classes, one of 4 math classes, and one of 2 English classes. We're basically making 3 decisions. How many different ways can we make the first 3? How many for the second? 4. And how many for the third? 2. So we take that, and due to the fact that these decisions are related, we would multiply together. How many different ways could we register for 3 courses? Well, that'd be 24. Okay, now another unique, and I think someone's doing an IA on something like this. Yeah, something with paths. But how many different ways could I get from A to D? Well, how many different ways through C? How many? I got 4 here, right? And I've got 3 here. So how many different ways would that be? 12 that direction. How many different ways through B? 2 and 3. I've got 6. And in this case, we're going to take the 6 and the 12, and we're going to add them. So there's 18 different ways. Okay, can you see how registering for classes, you're registering for 3 classes by making 3 decisions consecutively. But to get from A to D, there's 2 separate stems, right? I could go either this upper route, 6 different ways, or the lower route, 12 different ways. That's why I'm going to add those. Commonly, though, the general formula for trials with N1 events, then N2 events, then N3 events, kind of like picking your classes over there, would be N1, or the number of ways to pick that, times the number of ways, times the number of ways to pick the third. Multiplication principle, okay? So? Okay. This is fun because, well, it's not always clear. Yes, Wyatt? Okay, so permutations, right? Let's talk about the most basic of permutations. That is, I'm going to take a certain number of objects and put them into a certain number of seats, right? So let's take 5 seats, and we've got 5 people. How many different ways could I put those 5 people in those 5 seats? Or let's say 7 people in 7 seats. Okay, so I have 1, 2, 3, 4, 5, 6, 7. How many people could sit in the first seat? 7. Then 6. Multiplication principle right here. Okay, now I'm going to take away 4 of those seats, it looks like. So there's only 3 seats. How many people could sit in the first seat? 7, 6, and 5. Well, what is 7 times 6 times 5? That's really 7 times 6, or 7 factorial over what? 4 factorial. And that's how whoever came up with this came up with the formula. Well, they saw 7 items being placed into 3 seats. So they said 7 permutations of 3 objects would be equal to 7 factorial over, how do I get 4 factorial? 7 minus 3 factorial. So that would be 7 times 6 times 5. The general formula for NPR will be n factorial over n minus r factorial. Okay, and that comes out to be, what is that, 30 times 7, 210 maybe? Is that right? So permutations, order matters. Okay, combinations, how's that different? Okay, so combinations are a permutation, except it negates a certain number of those permutations. So for example, let's say, just for the fun of this, we had Emily, Carl, Gabe sitting in those 3 seats. Right? I'm just going to consider this subset. Okay, I could have Emily, Gabe, Carl, then Gabe, Emily, Carl, then Gabe, Carl, Emily. This is where my brain starts to hurt. Then Carl, Emily, Gabe, and Carl, Gabe, Emily. How many? 6 different ways. Now that will happen with every group of 3 that's put in there. So really all I have to do is I'd have to take what we knew before, 7 times 6 times 5, and divide it by, in this case, 6. Or, how could I write 6? It'd be 3 factorial. So the formula for combinations is the same as the formula for permutations, which is NPR, but divided by how many are being chosen factorial. What? So let's see what that looks like. What was NPR? NPR was n factorial over n minus r factorial divided by r factorial. If I divide by something, that's the same as multiplying by 1 over that. And does anybody recognize this formula? I mean, you just do combinations, permutations on your free time, don't you? Cha? Yeah, that is the combination formula. I can take all the permutations and then divide by the number of ways that I could organize only the ones chosen. That's what it is. Pretty good? So instead of 210 like we had before, because there's 6 different ways to do each of those permutations, we divide by 6, and it looks like there's only 35 combinations. Good? Okay. All right, cool. All right, let's move on to what if there's repetition? Okay, so repetition is pretty cool. You just take, let's say we're taking these 4 items, and we want to know how many permutation or how many different ways I could organize these items. Right? How many different ways could I organize 4 items? I'm selecting all 4. What would that be? How many different ways could I place a piece of fruit in the first row or in the first spot? 4, then 3, yep, then 2, then 1. Okay, but what if the apple repeats and they're identical in every way? Okay, so I could have orange. Watch this. This is techie. You ready? I made an infinite cloner. Yeah, so I could have orange, apple, apple, banana. I could have orange, apple, apple, banana, apple, apple, orange. Okay, so this is where it's going to get crazy, okay? I could have apple, apple, oh goodness. Orange, banana. I could have apple, apple, banana, orange. Let's keep going. I could have apple, apple, banana, orange. I could have apple, apple, orange, banana. Whew, let's keep going. I could have the 2 apples at the end. Banana, orange. Oh gosh. I could have apple, apple, banana, orange in that way. What have I missed? Oh, I got to split them up. I could have apple, apple, orange, banana. I could have apple, apple, banana, orange. This infinite cloner is making my shoulder burn. Okay, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I don't want to get lopsided here and have gymnast arm on one side and oh, whoops, sorry. That is so offensive. Apple, apple, banana. Hey, Cole, did you understand what I was saying last night on that Schoology thing?
I read that.
Did it make sense?
Put 2 chairs together and put them in
I decided to just hang from the railing on my stairs.
That'll work. Okay, have I covered all my bases here? Assuming that the apples are identical. So I've got 2 in the middle, 2 in the middle, 2 at front, 2 at front. On opposite ends, alternating the apple or the banana and orange. Of course, that's green because the yellow wouldn't show up. So green bananas, that makes sense. Okay, right? So I've hit all options. Right? We're assuming. So how many is that? 1, 2, 12. How in the heck would I get 12? There's got to be an easier way.
4 times 3.
4 times 3. Yes. But instead of 4 factorial, how many apples do I have? 2. I take that number of items, like I have 2 apples, I take 2 factorial. And I divide. That is the repetition rule. So let's take that and use it on another example. All right, so give me a word that has a lot of repeat letters. Mississippi, okay. How many different ways? There's 2, S-I-P-P-I. Okay, 11 letters, right? So the number of different ways I could arrange that would be 11 factorial. However, we have some repeats. Just to make this clear, how many M's do I have? Okay, so that wouldn't change anything. How many I's? How many S's? And 2 P's. And that right there, if we simplified it, would be our answer to the number of different ways we could uniquely organize the letters of Mississippi. Okay, let's look at a couple homework problems here. Number 3, how about that? There are 4 letters to be placed in 4 letter boxes. I don't know why they do that. In how many ways can these letters be mailed if only 1 letter is allowed per box? Part A, how many ways could how many different letters could I put in the first box? 4, then 3, 2, 1. That's just 4 factorial. Or 4p4. Right? 4p4. What would that be? That'd be 4 factorial. Some of you aren't going to like this. Over, what would I do? 4 minus 4 factorial. Okay, so 4 factorial we know is 24. 0 factorial by definition is 1. Okay. All right, part B. Part B. There is no restriction on the number of letters per box. So how many could I put in the first box? How many could I put in the second box? How many in the third? That's 4 to the fourth, which is 256 different ways. Because 4 to the fourth is 16 to the second. Yeah. So we've got our 3 Italian books. We've got our 2 chemistry books. Again, not guaranteed they're the same. And then 4 physics books. I almost put an F there. Almost. Okay, now we have 9 books. So if we're just tossing books up on the shelf for part A, and there's no restriction as to where they are, we would take 9 times 8 times 7 times 6 times 5 times 4, all the way down to 1. Right? What's 9 factorial? I don't know. Somebody. Okay, so that many different ways to organize those books. Now, what we're going to do is we're going to take, and in part B, we are going to ensure that the chemistry books stay together. So now how many things am I organizing? 8. However, those 8 items, how many different ways, or those 8 spots, how many different ways could I organize the chemistry books? 2 factorial. Now, some have been confused into thinking, should I divide by that? No, those chemistry books are not necessarily exactly the same. If they were exactly the same, then we would. Well, actually, we wouldn't, because we'd already taken care of it, and it wouldn't matter in that case because of the fact that there's 8 items. But we would multiply in that case. And so that would be, I don't know what that is. Somebody have an answer for that? I heard the 640. What is it? 80,640? Okay, cool. Okay, now let's say we group everything. All right, all books have to stay with their friends. Okay, that means how many items am I going to be organizing? 3. But how many different ways could I organize the Italian books? Well, 6, which is 3 factorial. How many different ways for the chemistry? And, of course, the physics. Somebody have an answer? 1728.